Hi students, this is Mr. Bob. In this video that you're about to see, you're going to see me walk you through how I expect you to take notes from the textbook. Now I know most students, when they think about taking notes from a textbook, they just kind of basically groan because it's a laborious process and not quite sure what to do. So that's why I'm walking you through this to show you my expectations. And hopefully you'll be pleasantly surprised that maybe it's not as onerous as you might think. I'm actually going to give you some pointers on how to minimize the amount of time you have to spend on it, and you certainly don't have to read every word of a science textbook. You probably shouldn't. And I also want to let you know that students have come back to me who have graduated and who have told me that this strategy that I'm talking about here, where you take notes and then you kind of revisit the material, this is an idea, space practice, you've probably heard me say, that is really powerful, and it's actually really helped them in their classes at the next level. So enjoy the video, and we'll be talking more about this in the future. Thanks.
Hi students, this is Mr. Bob. In this video, I'm going to show you how I would like you to take notes from the book. And even though I'm doing this for one particular HL physics unit, this could apply to any sort of physics class, and honestly any class, any academic class you have. Certainly like another science and possibly a math class. And so just to give you the setup here, if you are in my HL physics class, then this is actually the first assignment of this year. But again, this could apply beyond just those students. So notice what I've got set up here is I've got my journal or comp book or loose leaf pieces of paper if you prefer. I have set them up in a way, it's called a focus note fashion, also sometimes known as Cornell notes. This works for me. If some other format works for you, great. But I find it's really helpful to basically establish the line at the top, line about a third of the way down the left side, line at the bottom. The line at the bottom, we'll talk about what happens here later. But basically, you're going to take the first set of notes here, the first pass through the textbook, and then you're going to fill in or kind of revisit the notes in the coming days. This EQ stands for essential question. I don't have one to give you at this point. Sometimes that can be filled in at the end. Ideally, in the beginning, it's better to fill that in. But for this session, I'm just going to fill that in later on. Okay, so let's get right into it. This also assumes that you either have the textbook or an electronic copy, okay? Those of you who are here at the start of 2020, you're gonna have an electronic copy available to you. And you should have the electronic copy open to page 384. That's the start of chapter 14. So I don't know if anyone has ever told you, but reading or taking notes from a science textbook is not the same as like reading an English novel. You do not need to read word for word. If you want to read word for word, that's great. There's a lot of good information. This Giancoli book, I think, lends itself to reading word for word better than other science textbooks. But to get the information, the absolute essential information you need, you don't need to read word for word. And I am not going to read word for word in this video. So if you recall, on the sheet that I've given you, there are two main things you want to look at when you look at the sections that I ask you to take notes on. One is vocabulary that is bolded, and two is equations that are figured prominently in the text. You know, equations figured prominently will be centered. There'll be paragraphs either before or after talking about them. So we're going to look at those two things and try and get that done for sections 14.1, 14.2, and 14.3. So let's jump right into it. So I'm going to scan this, right? And again, I could read all this when a pot of cold water is placed, but I'm not. I don't see any bold-faced words. I don't see any sort of equations. So I'm just going to skip over here until I get to the first bold-faced word, and it's calorie. But if you recall in the assignment that I gave you, I said, let's not worry about calories because calorie is not an SI unit. It's a British unit. So we're going to skip this whole section of calorie and conversions from joules to calories because, again, that doesn't worry us here in the IB world. I do see here the word heat, and that seems like an important word. And so what I'm going to do is I'm going to read just the sentence before. Rather, heat refers to a transfer of energy. When heat flows from a hot object to a cooler one, it is energy that is being transferred from the hot to the cold object. Thus, heat is energy transferred from one object to another because of a difference in temperature. Okay, I think that's my first thing. I'm going to call this heat, okay? And then I'm going to just write the words. If I can paraphrase, that's even better. And I'm going to also abbreviate energy transferred, exferred, from one object to another. because diff in temp. Notice I've abbreviated a lot, but I still can get the meaning of it, okay? So let me just make sure I move this in a little bit further so hopefully you can see that. There we go. Okay. Okay, so there we go. In SI units, the unit for heat as any form of energy is the joule. Okay, that's probably an important thing to remind myself of. Also, at this point, I'm gonna do something that's really important. I'm not gonna scrunch all my notes up in a short amount of time frame, in a small amount of space. I'm going to basically skip a line or two. SI unit, joule, J parentheses, okay? I keep going. It talks about the ladder is still handy. 1 calorie raises 1 kilocalorie raises 1 kilogram. Okay, that looks like stuff that I really don't need to make sure I understand. Again, I want to emphasize, if you want to read in full what's going on there, great. It is helpful, but not necessary for what I'm asking you to do. Then there's an example here, working off the extra calories. I'm just looking at it. It looks like I could read through the examples. Sometimes those are helpful. I'm going to skip it for this video because I'm just trying to do exactly what the minimum that I want you to do. Okay, so that's 14-1. So 14-2 starts and we talk about internal energy. So you know what else I'm gonna do? I'm just gonna put, to give this heading a little bit more specificity, I'm going to put the labels of the headings. So heat, it looks like this one says internal energy. And the third one is specific heat, okay? So those three things, I'm just gonna list as part of my title because those seem to be important enough that the author titled them for different sections. Okay, so now we're at 14-2, internal energy. It says the sum total of all the energy of the molecules and objects is called as internal energy. Okay, that sounds like it's important, so I'm gonna write that down. Internal energy. By the way, if you wanted to get fancy, you could have like a different colored pen or something, or some way. Notice I'm underlining the vocabulary words twice, just kind of make them stand out. So this would be sum total of all energy of all molecules in object. And it looks like sometimes thermal energy. So I'm going to put in brackets here, thermal energy, because that sounds like it's a synonym for internal energy. Okay, then I read down here. Distinguishing temperature, heat, and internal energy. Using the kinetic theory, we can make a clear distinction between temperature, heat, and internal energy. Temperature is a measure of the average kinetic energy of the individual molecules. Internal energy refers to the total energy of the molecules. Thus, thus two equal mass hot ingots of iron may have the same temperature, but two of them have twice as much thermal energy as one does. Heat finally refers to a transfer of energy. Okay, so none of this is in bold, but I am just going to say, it seems like temperature is a pretty important thing to remember. So temperature is measure of average, AVG, kinetic, KIN. I could just label that KE, okay? Of individual molecules. Okay, and I'm gonna abbreviate molecules. So now we have our three things: heat, internal energy, temperature. Okay, and it looks like hopefully we can distinguish between the three. If you want to add the example that they provided, that might be good, but it's not necessary. Heat flows from water. So one thing it looks like up here when I look down at this paragraph is it seems to suggest that heat always flows from warm to cold. Okay, heat flows from warm, meaning the object with higher temperature, to cold. So I'm adding that. Notice that it's important that I left that space so I can kind of add that little comment up there. Okay? Then I get over here to the top of page 387, or bottom of 386, top of 387, and it says, let us calculate the internal energy of n moles of an ideal monatomic gas. The internal energy U is the sum of the translational kinetic energies of the atoms. Whoa. Okay? The sum is just equal to the average of the kinetic energy per molecule times the total number of molecules. Okay? So this looks important. This equation, notice this equation is got a label, it's like in a different color, so that looks really important. So So I'm going to write it down here. U equals 3/2 nRT. Whenever I have an equation, I'm going to right away give myself space to kind of, with arrows, to kind of show what are each of these symbols, what do they stand for, and what units are they used in, because that's really important. So it looks like N is number of moles. Okay. U, we said, was internal energy. And then what's interesting about this section is they refer to a previous section. They don't tell us explicitly what T and R are. So I'm going to actually put little boxes here, and I'm going to kind of say, hey, I need to go back to this because this section refers me to another section that I don't want to go to right now, but I need to figure out what capital R and capital T mean. Okay? All right. So we're done with 14-2. Finally, 14-3, specific heat. Okay. And I'm just going to quickly scan here. If heat flows into an object, the object's temperature rises. But how does temperature rise? That depends on the heat. The amount of heat Q required to change the temperature of a given material is proportional to the mass. Temperature change. Okay, so it looks like we have a specific heat equation. So I'm just going to call this, I'm going to put this equation Q equals MC delta T. Hottest rapper west of the Mississippi. Just kidding. So C, it looks like, is a quantity called specific heat. Okay? And it looks like Q is, it looks like from reading it, Q is heat. We could call it heat energy. Okay, so that's going to be in joules. We know that the energy, the SI unit for energy is joules. Specific heat, I'm not going to put the units on that just yet. Delta T, looks like that's change in temp, which probably gives me a clue back here. I can go quickly and say, okay, it looks like capital T is temperature. So this is temperature. We'll have to figure out what units those are in, okay? And that's gonna be important, but it doesn't tell me right away. And I'm gonna go back to my notes back here. So change in temp. It looks like over here, the delta T can be in Celsius, so I'm just gonna put Celsius, okay. You'll see that there are sometimes when Celsius is okay, but there are other times when you have to use something else called Kelvin. And so the specific heat has the specified units of joules per kilogram per degree Celsius. Oh, so that's the last one we don't have. M is mass, and that would be in kilograms because that's the SI unit. So this looks like a specific heat capacity or specific heat equation, if we want to call it. It doesn't have a name. I'm just going to kind of give it that name. Okay. I could look through this example. There's some good stuff there. But for the purpose of this video, I'm not. I'm just going to flip over here. And I look down here. I don't see... Again, I could read through all this. It's a good idea to read through all this. But for the purpose of this video, I do want to look at this table. Okay? Because tables are always good to take a look at and just get a sense. So it looks like specific heats of gases. It's talking about specific heats of different gases, which again, the specific heat you can think of as a way, as I read here, basically specific heat is the amount of energy required to raise a certain amount of substance by a certain temperature, right? Because it's joules per kilogram degrees Celsius. So the specific heats, and I actually missed this table, the specific heats here are given for different substances. It would be helpful for me to just look at it and get a sense. One of the things I might notice is that the specific heat for water, wow, look at that. Big numbers, really big numbers, okay? Much bigger than a lot of these other numbers. So anyway, that's something to look at. So it is a good idea to glance at tables. So for the purpose of this video, we are done taking the initial set of notes from 14-1 to 14-3. Just know that I revisit these notes, and I will expect you to revisit these notes, and those will be subjects of other videos. That's it.